pause. So shall I share my screen? Okay, can you see my screen now?
Yes.
Great. Okay, thank you for inviting me to the seminar. So first of all, I want to acknowledge the land I live and work as well. This land has been the traditional land of the Huron-Wendat and Seneca and the Mississauga of Credit for thousands of years. Today, this land is still home of many indigenous people from across the total island. And I'm grateful to have the opportunity to live and work here. So before my talk, I just want to understand about the background of my audience about a job exposure metric, which I call it a JEM. So may I ask, do you know what is the JEM is? So the pool, Angela will launch the first question, the first pool question, please. Thank you. So look like many of you don't know what the JEM is. So, and some of you may know what a JEM is. And yep, I hope my talk will give you some knowledge of how to develop a germ and how a germ can be useful for occupational AB research. Okay, we can close the pool question. So today I will present a part of my work at OCRC, which is developing an industrial specific silica job exposure matrix for mining using historical exposure measurement in Ontario. So silica is one of the major elements of Earth crust and can be found in rock, sand, stone, concrete, ceramic, glass, and other industrial materials. In 2016, CARES Canada estimated that there are 429,000 Canadian workers were exposed to silica. So among those workers, 27% of them were workers working in mining and quarrying industry. So in other words, mining and quarrying is the industry have a second highest number of workers exposed to silica at work. So the exposure to silica at work can cause various respiratory diseases such as silicosis, chronic obstructive pulmonary disease, and lung cancer. In a report of abundance of cancer in Ontario, there are annually 200 lung cancer cases related to silica exposure at work. Occupational exposure to silica can also cause other diseases such as the autoimmune and chronic disease. So to support the AP study of occupational disease, especially for the chronic disease, exposure data is an essential resource to assess the dose and response relationship. To estimate hazard exposure, job exposure metric is one of the tools we can use when the individual's measurements are not available and or practical to collect. So here on the left-hand side of the table, is a simple example of germ with three axes: industry, occupation, and exposure agent axis. The germ cells contains the information, exposure information of each combination of industry, occupation, and exposure agent. The germ cells can contain various information, such as whether hazard is present or absent, number of people exposed to that hazard, an average standard deviation of exposure measurements for each combination. Job exposure metric offers some advantage over other exposure assessment methods, such as its lower cost than the expert assessment method. The JEM also provide a flexibility, so it can provide us a wide applicability. Other advantages of the JEM are that it can avoid the bias of record and social desirability, which can happen with the self-reporting method. And also, the JEM can provide ability to estimate exposure based on job title when no other exposure data is available. So one disadvantage of the job exposure metric is that this method cannot account for individual variation in exposure within the same job title. But however, this advantage can be overcome by the advantage of the JEM can offer. So currently, most JEM used to estimate the exposure to hazard for mining industry is a generic JEM using data from general population. So it means those JEM are lack of specific information related to the job and the industry. Currently, to the best of our knowledge, no industry-specific job exposure metric for silica is available in North America. And in order to build the JEM, we need to have the information of exposure measurement. So in Ontario, we have Ontario Mining Exposure Database, which we call as OMED. This database is a great source for mining exposure data. This database was created by digitalized and centralized more than 4,000 hard copy of exposure data collected by various sources, such as government agency and ministry, mining companies, and consultants. The final giant database contains more than 118,000 exposure measurements of 183 hazards collect over 45 years between 1950 and 1999. This database is very rich in data. It includes information of mines where samples were taken. For example, it includes name of mining company, location of the mine, primary and secondary ore type of a mine, and so on. And the database also contains the information of the sample. For example, sample type is the area of personal sample location, whether it's the surface or underground sample, and type of the hazard. And it also includes the job title and job task associated with a sample. So, but however, the job title in this OMED database were in a free text format and need to be standardized. So for our study, we aim to develop an industry-specific silica JEM using the historical exposure data in OMED. And we also want to investigate the effectiveness of the auto job coding programs of OMED free text job titles. And we want to evaluate the impact of incorporating the US mining exposure data into our OMED on an exposure estimate. So here is the flow chart of how we develop the job exposure metrics using historical measurement in OMED database. So in the first step, we extracting the respirable crystallized silica from OMED. We were able to extract 557 aggregate samples and more than 11,500 individual samples taken from 147 Ontario mines over 30 years between 1962 and 1992. The aggregate sample contains a summary of individual exposure were then cleaned and simulated by using Monte Carlo Simulation to provide 20 sets of simulated individual samples. These simulated individual samples from each set were combined with original individual samples to create the final data set of more than 19,000 exposure measurements. This is a lot of data for a single exposure agent in the specific industry like mining. So from this final data set, to come up with individual silica germ, we calculate the exposure estimate for each germ with a minimum of 10 sample per germ cell. It means that if the germ cell have less than 10 sample, we will not report the exposure estimate for that cell. So this process repeat 20 times of the new sets of simulated data, and then a summary measurements of 20 individual samples were calculated to come up with a silica industry specific germ. So when coming with OMED germ with criteria minimum 10 sample per germ cell, we lost information of some germ cell. So we thought of incorporating US mining exposure data into our OMED germ to improve our OMED germ. The US Mine Safety and Health Administration, called as MSHA, has been frequently collecting mining exposure data for compliance and monitoring purpose since 1980 up to the present. All exposure-related data from 2000 can be obtained online via their website, but the data before 2000 need to be requested via FOA. However, it seems like currently MSHA no longer provide information for exposure measurement before 2000. So we have to search in the literature to find out whether any study report MSHA as silica exposure data before 2000. We found two studies conducted by NIOSH researcher reported silica exposure in US mice in the period of 1982 to 2017. And we were lucky that they were happy to share the raw data with us. So that's how we got 366,000 MSHA silica exposure measurement from NIOSH. So similar to OMED, MSHA data is also include information of the mice, samples, and job title. But the difference is the job title in MSHA data were standardized, not in a free text format like OMED. So before coming to next slide, I will have a question for you. Have you ever done job coding for any projects? Angela, can you help me to launch the second question? Well, it looks like most of you haven't done the job coding for any project yet. Okay, so next slide, I think I can give you some information on how job and industry will be coded. So after gathering exposure data from OMED and MSHA, I assigned a standardized industry and occupational code. Industry code were assigned based on primary commodity or of the mines using the US version of Standard Industrial Classification Code 1987 and North America Industry Classification Code 2017, which we call as SIC and NACS. And for occupational codes, we use the US version of Standard Occupational Classification Codes version 2010 to standardize the free text job title. And we also crosswalk the MSHA standardized job title to US stock 2010. So two methods we use in our study for assigned occupational codes. First one was manual job coding method, for which two trained coder will independently assign the source code based on the job title and their understanding of a mining industry, and the ties between two codes will be decided by the third coders. This method is used as a gold standard for job coding, but the disadvantage of this method is time consuming and resource intensive. So with the advancement of computer science and machine learning in the past decades, auto job coding method can potentially be an alternative option for the job coding task. Two publicly available auto coding programs, which as Soxer and Knox, were used in our study. For both programs, information of industry and occupations of such as job title and job task were inputted. And then the program provides us the source code together with the confidence score, indicate that how correct the program thinks that the code could be. So the advantage of this coding is that it's much faster and less expensive compared to the manual job coding. But however, the accuracy of this result from this method, the result of this method depend on the complexity and specificity of the job information we input in. So after assigning the industry and occupational codes, we calculate kappa to assess the agreement between manual coders and between the auto coding programs. Kappa will also calculate, assess the agreement of manual coder and auto coding programs. The correlation were used to evaluate the impacts of incorporating MSHA data into our OMS germ on exposure estimates. So when developing a germ, we can calculate many different metrics. However, in this presentation, I calculate the number of samples and exposure intensities, including average, standard deviation, geometric mean, and geometric standard deviation of exposure measurements. Here are some results we got from our OMS germ. So for overview, this pie chart shows the composition of our OMS samples. Among 19,000 silica exposure measurements, the majority of them came from government agency and ministry, and then 28% from companies and other 7% from other sources. 2/3 of OMS silica samples were personal samples. So our OMS database is so rich in data with many variables. Because of this, we can have the flexibility to make a germ with multiple axes. So these are example of some variable we can use as axes to develop our OMS germ, like commodity, time periods ranging from 1960 to 1992, sample location indicate that sample were taken either from underground or surface, geographical area of the mines. We have information of silica exposure from mines in 10 different Ontario areas. And then we have a standardized job title with 115 unique job titles and standardized job code with 20 different mining industry. The number of germ cells depend on variables or axes that we select. So here, for example, if we combine commodity and time period axis, we will have 48 germ cells. But then if we add a geographical area in that combination of commodity and time period, we will have 71 germ cells. And here's the example of our OMS germ cell with three axes: time period, sample location, and a commodity. So if now we select the selected clay mining with sample taken from surface in the period of 1988 to 1992, and we will have 223 workers exposed to silica for that combination. And in the next box, we will see the calculated average and standard deviation, geometric mean, geometric standard deviation of the selected combination. So in this example, I pick time periods, sample location, and commodity as an example. But a JEM can offer the flexibility that as such you can pick other axes. For example, instead of time periods, you can put geographic areas in or 6 code in to get another germ, another germ cell, get information of another germ cell. And that very depend on your research interest to select which axis you want to see the result. So many times people prefer to use a personal sample because personal sample are thought to be better reflect the worker's exposure. So we investigate the impact of restricting our OMS germ to only personal samples. So as a result, you see here, the number of germ cells were reduced by when we restrict the data to only personal samples. For example, the combination of commodity and time periods using the full data set provide 44 germ cells, while there are only 90 or 39 germ cells if we restrict to personal sample only. So here's come to some preliminary result of job coding performance. So now let's see how well different job coding methods agree with each other. First, this is the result of agreement between two coders. Kappa were calculated to assess the agreement of stock code assigned by two coders. Kappa less than 0 mean poor agreement. Old boy is 65 is a substantial agreement. As we see here, the agreement between two coders was poor for OMS job title and substantial for MSHA jobs titles. So the result is understandable. Since more standardized job title is more standardized job title is, the higher agreement between coders. So this is a new finding, and some of the reason to explain the poor agreement between the coder of OMS job title, we think of different in skill level and background of the coder, and OMS has some vague job title. So for the next step, we will get a third rater to do all the job coding and then assess the agreement between the third rater with other raters, like all the coder. Along with assessing the agreement between two manual coder, we also assess the performance of auto coding programs on a unique job title. This program provides confidence score for each source code they assign for a job title. So the vertical axis here represents the proportion of source codes with confidence score greater than 0.5. It means that the program thinks that 50% of chance that source code they assign for the job title is correct. If we see that Knox program, we see here that the Knox program was able to assign the source code for more than 60% of input job title with confidence score greater than 0.5. This source, while source is less confident in source codes, is assigned for input job title. And beside that, we can observe the same pattern as a result of manual job coding. Both programs perform better with more standardized job title like the job title in MSHA data. So after comparing two coders and two auto job coding programs, finally we assess the agreement between auto coding programs and the manual coder. So I must admit that it's a bit shocking for even me and my co-author when see that result that job codes assigned by Knox shows zero agreement with both coders. While then in the previous slide, Knox show high confidence in source code it assigned. So we really didn't expect that because we hope that at least Knox showed a fair agreement with either coders in OMED job title since they were poor agreement of menu coders for OMED job title. This means that there were two different job title from two different set of job title from coder, and the Knox agree with none of them. So since we got this result 2 days ago, we haven't had enough time to investigate further on this, but we will. And for structure, there are better agreement for MSHA and OMED job title, similar to result we saw between raters earlier. This probably due to the fact that MSHA job title were standardized. And here, as we expect, at least for coder 1, we see the improvement in agreement when we restrict to data to only job with a high confidence score, which is greater than or equal 0.5. So now it's come to the result of our last research objective, which is evaluate the impact of incorporating MSHA data into our OMED germ. Before coming to this result, Angela, can you help me to launch the third question? Thank you. So may I ask you, from your expectation, how comparable will MSHA and OMED exposure result be? All right, interesting. Most more of you think it's not comparable, and well, this following result was just calculated this week, so I'm excited to show it to you. Let's see it together whether it's MSHA and OMS is comparable or not. We can use MSHA data or not. Okay. So this graph show the comparison of annual silica average from OMED and MSHA data. The red line here represents the current Ontario exposure limit. I think BC have a lower exposure limit, it's around 0.05. But for Ontario, it's still high, like 0.1 milligram per meter cube. So now we can see here, at least at the early year, silica exposure were high in both OMED and MSHA data and decreased throughout the years. And in the periods of 1982 and 1992, when the OMED and MSHA data overlap, yeah, the exposure concentration of silica in OMED and MSHA were kind of comparable. However, it should be noted that in this chart contain the silica exposure across all jobs, all industry, and sample type and sample location, so on. So now let's take a look closer to compare silica exposure stratified by sample location. So this graph show average silica exposure of OMED and MSHA data samples taken from surface and underground. So in the period of 1982 and 1992, when OMED and MSHA data overlap, silica exposure level in both data tests were comparable for surface sample. But for undergraduate underground samples, sorry, there were slightly higher exposure level in MSHA underground samples compared to OMED underground sample. However, both datasets showed a decrease in trend over time for both surface and underground sample. This provides some confidence in the success of incorporating MSHA into OMED data. So then we go ahead and incorporate MSHA data into OMED data. We assess the relationship of annual exposure concentration from OMED germ and OMED MSHA germ by using a Spearman correlation. This plot here shows the relationship between annual exposure concentration from OMED germ and MSHA germ and OMED MSHA germ between 1982 and 1992, when exposure overlap in both databases. The Spearman coefficient is 0.39, it show the fair correlation between exposure level estimate from OMED germ and OMED MSHA germ. However, please note this. This is the result of annual average across on job and commodity and industry. We will investigate it further with other variables, and we will look at the different axis combination as well. So to evaluate the impact of incorporating MSHA exposure data into our OMED germ. So one of the main purpose of adding MSHA data into OMED germ is increasing the number of germ cells in the OMED germ. So in this result, we can see that number of cells increase a lot when incorporate MSHA into OMED germ. For example, look at the combination of sample location and year. The numbers of germ cells increase 3 times when incorporating MSHA data into OMED germ. And for 3-axis combination, the number of germ cell increase 2 times with the addition of MSHA data into OMED germ. So these results were only preliminary results, but it looked very promising to incorporate MSHA data into OMED germ. So to conclude my presentation, we were able to provide the first silica industry specific germ for mining industry with a flexibility of multiple axes available. And we will continue to investigate further on the use of auto coding programs. But for our result, SOXA may be a better auto coding program for our data. And so far, the result look very promising to incorporating the MSHA data into our OMED germ to provide a germ generalizable to the wider geographic area. So next step, we can develop a more industry-specific germ for other mining exposure, for example, like dust, nickel, copper, so on, using an MSHA and OMED database. This germ can provide exposure measurement to improve the understanding of exposure disease relationship for the long latency disease such as lung cancer. So yeah, hope you have learned something new in my talk. And now I'm happy to answer any question if you have any question.